All right, good morning, everyone. Welcome back to class. So we are going to start a new chapter, our sixth and final chapter today. Today it's the 21st of November, so we're right on track with everything. Exam 4 is closed. And so let's see, how many more days of class? We just have 4 more days of class, actually. Next Thursday's Thanksgiving break, so we just have today, Tuesday, then Tuesday, Thursday. Okay. Um, I'm not sure how much time we'll have to review on that last day of class. It kind of depends on how fast we get through chapter 6. Sometimes we'll have that day to review, sometimes we won't. So I did post an announcement today. See, at least I think I had posted it. Maybe it's scheduled to go out later. Let me go ahead and post it right now so you can see this. Um, so they're going to do, looks like 4 different review sessions for you guys on the various campuses. So let me just see if I can get this to go out right now. Okay, so December 4th, they have one at the South City campus, and then December 2nd, 3rd, and that's probably supposed to say the 4th. It looks like they have one at the Redwood campus. Okay, so those all be helpful to go to. I would encourage you to go to maybe one of them, and definitely to one of them, maybe two, um, and so that'll help, I think. Okay, so that's available to you, and then just like I do for the other exams, I'll post a review video from one of my online classes. So anyway, that's coming up. The final is comprehensive. It'll be over chapters 1 through 6. And remember, you have to get at least a 50% on the final to get higher than a D in the class. So that 50%, so what it means is if you get 49% or less, there's a ceiling of a D on your grade. So your grade can't go any higher than a D. It can go lower, of course, but it can't go any higher than a D. Okay, so just keep that in mind as you're preparing for the final. Do you guys have any questions for me as we get going with our last chapter? Anything I can help you with from homework or quizzes, anything at all? All right, well, let's get going then with our last chapter. Whoops, that's not you guys. We're actually, so here on page 160, we're not going to start chapter 6 just yet. What I want to do is offer you a way of kind of organizing all of the different procedures, all of the inference procedures we've talked about this semester. Okay, so each chapter we've had 2 or so new inference procedures, right? So back in chapter 3, we looked at the one sample z-test for proportion. Okay, so that was chapter maybe 2 and 3 actually. We did that. Okay, and then we did the z confidence interval for proportion. That was chapter 3. Then we did the one sample t-test for a mean. That was chapter 4. We did an interval for that. Then we did 2 means, right? So we did 3 of them in chapter 4. Actually, we did 4 of them. Okay, and then in chapter 5, which is what you guys just did in the 4th exam, it was the 2 sample z-test for difference of proportions, the 2 samples z confidence interval for difference of proportions. Okay, so on any one exam, you kind of know, what the 2 or 3 procedures will be. But by the time you get to the final, you're looking at like 8 or 9 different procedures, right? And so you have to have a way of organizing all of these procedures in your mind. Okay, and so that's what I want to practice with here is thinking about a research question and then trying to identify what procedure you would use to answer that. I like this for a couple of reasons. First, as I've mentioned, it's a great way of organizing the whole semester. Secondly, it's very much what it's like when you're doing real research. If you're consulting and doing statistical consulting for a researcher, that can be one of the hardest things to do is to figure out what is the appropriate kind of analysis to do for their research, okay, or to help them guide them with their research. So oh, and then there's a third reason I like it. You're going to see this kind of thing on the final. So there's a question on the final that very much looks like this kind of problem. So it's not, I'm not asking you to do the research here or to like actually calculate anything. I'm just asking you to identify what the correct procedure would be. Okay, and so let me give you an example here. So let's say the research question is we want to estimate the mean height of Salt Lake Community College students. Okay, so what kind of inference procedure would we use? Okay, and again, the list is above. Uh, we just looked at them, so there's like 8 or 9 of these procedures. Which one is the correct one for estimating the mean height of Salt Lake City community college students? Okay, so basically you're going to go through this list until you find the right one. Okay, so if you're talking about all students at the college, there's just one group, right? So it's not these, we're not looking at 2 variables. Height is quantitative, so it's not categorical. Okay, so it's going to be one of these 2, right? It's either going to be the t-test for a mean or the confidence interval for a mean. So which one is which? When do you use a test? When do you use a confidence interval? Well, you use a test when there's a claim that you want to test out, right? You use a confidence interval when you're trying to estimate a parameter. Okay, so for this, for estimating the mean height of Salt Lake Community College students, it would therefore be a 1 sample t confidence interval for the mean. Okay, and so on the final, there'll be a problem like this. It'll have 3 or 4 of these research questions, and then on the other side, they'll have procedures, and you line up the procedure, identify the correct procedure for the research question. Okay, so it can get kind of tricky. So I want to, let's see, there's a question here in the chat. No, it's just the same number of notes, Killian. So 1 page of notes front and back, 1 sheet of paper front and back. Okay, so up until now, we've always worked with the version 1 formula card. Okay, and this is fine. You can still use this on the final, and it's a great formula card. But there is another formula card I want to show you. It's the same formulas, but it's organized differently. This one is organized sort of by chapter, whereas this version of the formula card is organized by procedure. And so if you want to use this one on the final, that's fine. You don't have to, but it is available for you. Let me show you where this is. It's in Canvas, so you can download this if you'd like. Go back to our home page here. And then if you scroll down to where it says formula cards, you can see this version 2 formula card right here. Okay, so I don't really think the version 2 is that great until you get to the very end of the class, and then I think it's quite useful, but it's up to you. I want to show you how you can use this to help you think about the correct inference procedure. Okay, so it's basically set up like a flow chart. So if you know how flow charts work, you've seen one of these before maybe. So you start in some position, and there's a question there. And you answer the question, right? So what type of variables are being studied? So if we're thinking about the height of students, height is quantitative, right? Height is the number of inches or centimeters tall you are. So it's not categorical. It is indeed quantitative. Okay, so we're not up there in the categorical, we're down in one of these. It's not 2 quantitative variables. Okay, height is a single variable, right? So let's see here. For some reason, my pen is being weird. 1 second here. Okay, so anyway, I'm trying to, there we go. For some reason, it's being super weird for me. 1 second here. Okay, so it's not 2 quantitative variables, it's height, right? And so are we looking at 1 group here or 2 groups? Well, it's just 1 group. It's all of the students at the college, right? So it's not 1 quantitative variable being compared across 2 groups. So we start here and we answer the question. It takes us over here, right? So that gives us a new position in the flowchart and another question. Does the research question ask for a value or to evaluate a claim? There should be a K there. So does the research question ask for a value or to evaluate a claim? So again, if we go back to that question, it's not making a claim. It's just saying, it's not saying that the mean height of SLIC students is 5'10" or something. It's just saying estimate it, right? So it's not a claim that we're testing. It's a value we're trying to find, right? So we're estimating a value. So what does that mean? It means we're not doing a test. It means we're doing a confidence interval. Okay, so it's a one sample T confidence interval for the mean. Okay, so it's a nice way of organizing all of the chapters really for the whole semester. So I really love this question here in the notes. So I want you guys to practice with this a little bit. Over here on page 160, I want you to try one of these. We don't have time for everybody to do every one. So let me kind of assign these out to you guys and just give it a try. Okay, so Armand, I'd like you to do this one. Devin, I want you to look at this one. Is the graduation rate higher for traditional students? Killian, I'd like you to do this one. Kylie, I'd like you to do this one here where you're looking at business students versus health science students. Lana, I'd like you to do this one here. Fabrita, if you could do this one. And then Sarai, Sarah, if you could do this one here, that'd be great. Okay, so read through your research question and see if you can identify the correct procedure that one would use to answer that question, okay? So I'll just go quiet for a couple minutes. And if you figure yours out, then feel free to jump into another one and try another one out. It can only help to do as many of these as you can, okay? As soon as you get your answer, if you could just put it in the chat, that would be great. All right, let's see here. So Devin is saying, okay, so Devin was looking at this one here. So is the graduation rate higher for traditional students at SLIC than non-traditional students? Okay, so let's see here. What is that one? It's a two sample z-test for a difference of proportions. Okay, why is that? Well, let's go through the flowchart, right? So we have this flowchart here. Let's clean it up a little bit and think about what is the correct procedure to answer the research question. Okay, so all right, let me repeat that. So we have traditional students at the college, we have non-traditional students. So oh, Devin's asking where we can find that flowchart. It's over here on the home page. So if you go back to the home page and you scroll down to where it says formula cards, there is a flowchart here. It's in this version 2 stats formula card. And it's all the same formulas as our normal formula card, but it's organized in a different way. And it's good for, it's a good way of thinking about it too. So anyway, that's where the formula card is. So yeah, let's go through that flow chart here and help us think about this. So traditional students, so who are traditional students? These are the students who graduate high school and either right away or maybe like a year or two later go to college, right? Non-traditional students are basically anything else, right? Everything else. So, you might graduate high school and then take like 10 years off from school and then go back, something like that, right? And so it's basically two groups, and we're looking at one variable across those two groups, graduation rate. Okay, so Graduation is a categorical kind of variable, right? Either somebody graduates or somebody doesn't graduate, right? So, so with that in mind, let's go over to the flow chart and work our way through it. So what type of variables are being studied? Well, it's categorical, right? It's not quantitative, okay? So we're not going to end up down there. It's going to be one of these two. So do we have one categorical variable or two? Well, we have two because there's two groups, right? The first categorical variable is graduate, yes or no. And the second variable is traditional student, yes or no. Okay, so we're here. So we jump up to here. We're not in here. And then we get to our next question. Does the research question ask for a value or to evaluate a claim? Well, it says, is the graduation rate higher for traditional students than non-traditional students? So that's basically a claim, right? So somebody's claiming that the graduation rate is higher for traditional students than for non-traditional students. Okay, so that's a claim, which means we're doing a test. So it's the two sample z-test for a difference of proportions. Does that make sense? Okay. And then let me just add in a couple of other things that might help. Words like is, can, do sort of indicate a claim, which means we'll be doing a hypothesis test. Words like estimate or what kind of indicate we're doing an estimate or trying to find a value, which means it would be a confidence interval. Okay, all right, great. So two down, we've got about 8 or 9 more to go here. So let's see, Armand is saying that he thinks his is a one sample z-test for proportion. So, so let's see here. Is the proportion of SLIC students who receive financial aid higher than 50%? Okay, so so let's see here. That is a one sample z-test for proportion. So very good. Yep, that's exactly right, Armand. So why is that? Okay, well, so every student here at the college either receives financial aid or they don't. They're not asking about how much financial aid. It's just saying do they get it or not. And then so there's some proportion of students that are getting it, and they're asking is that proportion higher than 50%? In other words, do a majority of students get financial aid? Okay, and then so how would we figure out the procedure? So let's go back to the flow chart. And by the way, if you don't like the flow chart, you don't have to use it. So what types of variables are being studied? Well, it's a rate. It's a graduation rate, right? So it's not quantitative. It's categorical, right? So we end up over here. Okay, so how many variables are we looking at? Well, it's just one group. It's all students at the college. We're not breaking it into traditional versus non-traditional here. So we just have one categorical variable. Okay, so we end up here. Then we get a new question. Does the research question ask for a value or to evaluate a claim? And it's saying, is the proportion higher than 50%? Okay, so that's like a claim, right? We're testing the claim that a majority of students are getting financial aid. Okay, so yeah, it takes us down to here to the hypothesis test. So it's a one sample z-test for proportion. Great, right? So, all right. Killian said one sample z-test for a proportion. It's a one sample t-test for a mean. So why is that? Well, let's think about the data here. We're looking at, so it says, do SLIC students drive faster than 15 miles per hour in the parking lot? Okay, what kind of data are we looking at? What kind of variables are we looking at here? Okay, so we come back to our main question. What type of variables are being studied? Well, it's speed, right? It's driving speed. So speed is quantitative. It's a number of miles per hour that you're driving, right? Okay, so It's quantitative, it's not categorical. Okay, so these are out up here. So it's one of these three down here. We're not ready for this one yet. That's chapter 6. So really, it's either one quantitative variable or two groups, right? So the same variable compared across two groups. So I don't see anything indicating here that we have two groups. It's just talking about all students. So we end up here in the one quantitative variable. Okay, so we start here, we end up here. Then we get a new question. Is this a hypothesis test or a confidence interval? Well, it says do, which we know is probably a test, right? And the claim is basically that that students are driving too fast in the parking lot, more or less, right? So it's a hypothesis test. So one sample t-test for a mean. Good. All right. Kind of tough at first, but once you get the hang of it, it's not too bad. And again, I think it's such a great way of organizing all the material. Okay, let's see. Kylie, did you get yours? Let's see, sample for confidence interval for difference of means. So I think you mean two sample, right? So two sample T confidence interval for difference of means. Perfect. Yep, good. Right. So what is the difference between the mean number of credits for SLIC students in the business school and the health sciences school? Okay, so we're looking at all of the students in the business school, all the students in the health sciences, and all of those students have some number of credits that they're taking. And we want to see what the difference is between the two schools. Maybe there's no difference, okay? Or maybe the business students take more than the health sciences, or maybe it's the reverse, right? And so we're trying to figure out what that difference is. Okay, so what kind of data do we have? Well, it's number of credits. Number of credits is quantitative. Okay, so it's quantitative data. Then we think about, how many groups there are. Well, there's two groups. Okay, so it's quantitative, and we're comparing one variable across two groups. So we're here. Then is this a confidence interval or a hypothesis test? Well, it says what is the difference, right? That indicates we're trying to estimate a number, right? So it's going to be an interval. So it's the two sample T confidence interval for difference of means. So very good. All right. Okay, and then Lana was next, I believe. Lana is saying this two sample t-test for difference of means. So is the number of hours worked per week lower for full-time SLIC students than for part-time students? Okay, so full-time students, these are students who are taking, I believe it's like 12 credit hours or more. Part-time students are students who are taking fewer, right? And so maybe that's due to, work, jobs and stuff, right? So the mean number of hours worked at a job, are the full-time students working less at a job outside of school than part-time students? Okay, so I believe you're correct there, Lana. It's the two sample t-test for difference of means. Great. Okay, so I think you guys are catching on to this. So what kind of variables are being studied? Well, it's the number of hours, which is quantitative. Okay, and we have two groups. We have the full-time versus part-time. So we're here, and then it's saying, is the mean lower, right? So it's like a claim disguised as a question, right? So it's a test. Good. So it's the two sample t-test for difference of means. Great. Okay. Any questions here about this? And then Pepita is saying, I think mine is the one sample z-test for proportion. Close. I think this one's an interval because it's saying estimate, but everything else is correct here. So estimate the proportion of students who transfer to a four-year university. Okay, so all the students here at the college either transfer to a four-year university, like the University of Utah or something, or they don't, okay? And so that is categorical. So we're looking at a categorical variable, okay? We just have one group here. We're looking at all students, okay? So it's a single variable, one group, categorical, and then it says to estimate, and that's telling us we have an interval. So it's a one sample Z confidence interval for the proportion. Okay, great. And then let's see, Sarah, did you get yours? Two sample. Good, it is two sample. What kind of data is this? So it's what's the difference between the percentage of students who pass 1040 and the percentage of students who pass biology 2320. So a lot of our stat students, not all, but many are taking some other biology courses. And so we're just kind of comparing, difficulty level between the two courses. So what kind of data is this? Well, it's a pass rate, right? So it's a percentage. So either a student will pass or not. So these are categorical. This is categorical data. And then so we know it's categorical, and then we look at how many groups there are. So there's two groups. There's the 1040 students and there's the 2320 students. So it's two sample, it's categorical. So then it says what is. So what is indicates that it's an interval. Okay, so it's a two sample Z confidence interval for difference of proportions. Great. So thanks for participating with that. One thing I would recommend doing before you get to the final is coming back to this page at some point, take a piece of paper and cover this procedure column and see if you can do it without looking at the answers. So just, take a piece of paper, cover up this procedures column and see if you can do this, okay? This number 2 up here is a topic we'll talk about in chapter 6, which is where we're headed right now. Any questions out there before we really get going with chapter 6? Okay, so we have some algebra for our 1045 students. Obviously, it doesn't apply to you guys so much. So I'm going to jump over here to page 163, and we'll have a look at our new chapter. So some of the stuff in chapter 6 is similar to what we've done before. Okay, we have the same kind of data. In this case, it's quantitative data. We're going to be looking at associations between variables. So we've talked about that before. We're going to be doing hypothesis testing. We've done that before. So what is new here? What's different? Well, what's different here is the type of the structure of the data that we have. Okay, so we've talked about quantitative variables, but we've never had two quantitative variables simultaneously. Okay, so it's the structure of the data that's different here. And so this kind of data is especially useful for understanding associations. Okay, and so we know what an association is. And so do we even need this definition here? Maybe, maybe not, but it doesn't hurt to have it. We say that two variables are associated when there's some connection between them. Okay, almost sounds like a circular definition, but so how do we go about analyzing this kind of data? Well, we begin with graphs. Okay, so we're going to pick up a new graph here in chapter 6, a couple new graphs actually. It's called the scatter plot. Okay, and so with the scatter plot, it's basically, if you remember from your algebra days, you have an x-axis, a y-axis. We call this the Cartesian plane, and you're going to draw a bunch of points in the Cartesian plane. Okay, and then we basically fit a line to the data. Okay, and we use the line to understand the pattern in the data. Okay, so that's what the scatter plot is. It's basically the data depicted as dots in the Cartesian plane. So let's just remind ourselves how the Cartesian plane works. We have points that are defined by coordinates. So we have an x value and a y value. Okay, and so 3, 5, we would go to 3 over 3 and then up 5, and we would have a point, right? Negative 2, 4, we would go over to the left, right? Negative, so again, to the right is positive, to the left is negative, up is positive, down is negative. Okay, so we go negative 2, 4, we would go 1, -1, 0, 2, -5, 0. Any questions about that? So that's a scatter plot. Okay, let me show you how to make the scatter plot in GeoGebra, because for real research, you wouldn't do too much by hand with a graph, right? You would take your data and throw it right into software. So let's do that. Let's pull up GeoGebra here and practice a little bit with that. So we go to the toggle, the 3 dots, probability calculator. Nope, sorry, not the probability calculator, the spreadsheet. Okay, so we open up our spreadsheet and we put the data into the spreadsheet. So I'm just going to use the same numbers that we just had. So we had the 3, -2, 1, 0, 5. Then we had the 5, 4, -1, 2, 0. So that's the data set from page 163. So we highlight the data, and we go over to the columns over here. And we've done quite a few different types of one variable analysis. This is the first time where we have two variable analysis. Okay, so we call it two variable regression analysis. So you're going to hit that button, and there you go, there's your scatter plot. Now it's a little bit unusual because when we look at scatter plots, we're accustomed to having an x and a y axis cross at 0, 0. That's not quite happening here. There's nothing wrong with this, it's just a little bit different is all. But it is the same scatter plot that we just drew, right? Okay, so the process is, if you're looking at this new kind of data set where you have quantitative and quantitative, and you're trying to understand the relationship, you start with a scatter plot. The scatter plot is an excellent visual way of quickly determining if you have a relationship and a relationship that's worth investigating further. Yes, that's right. The x-axis, so we do call these ordered pairs. The language is ordered pairs. So it's if you're using the letters x and y, then x will always go first. So order, we're typically talking about like an alphabetical order. Okay, does that answer your question, Lena? Good. So you get your data, right? It's coming from some experiment that you ran or some observational study that you did, and you put it into your software and you look at the scatter plots, right? So what is it that you look for in a scatter plot? Well, there's lots of things we look for, but the 4 things that I want you to focus in on are form, direction, strength, and outliers. So I want you to look for the form, the direction, the strength, and outliers. So what kinds of forms are there? Well, there's lots of different forms, okay? For our class, right, so for our intro stats class, we begin with the linear form. Okay, so it's the most basic, but it's super important, and it's the natural starting point. You wouldn't begin with like nonlinear because it's so much more complicated. So we begin with the linear form, and that's really about the only form we look into very much in this class. But if you take more stats classes, you'll learn about all sorts of nonlinear forms out there. It's quite an interesting topic. But anyway, so what I do is I actually look for nonlinear first. And so nonlinear is quite, there's quite a range of possibilities. But this one here, we see a curve in the data, right? So what I do, I get the scatter plot and I look for any sort of nonlinear pattern, okay? So nonlinear being, again, like a curve or like an elbow in the data, like a break or any sort of gaps in the data set. If I don't see any of that, then I will declare that it has, then I'll say it has a linear form to it, like a line, like a straight line, okay? So I kind of, to decide if it's linear, I sort of use this sort of negative approach. Does it not have, is it lacking nonlinear kind of behavior, okay? So that's the first one, is the form, the general pattern of the relationship. And for all the techniques we're going to learn in chapter 6, they only work for linear forms. So if you have a nonlinear form, then the techniques we study in chapter 6 don't really apply. Okay. The next thing we look for is the direction. Okay, so when you have a linear trend, typically it's either going to be going up, in which case we call it a positive trend, or it's going to be going down. You can have a trend where it's completely horizontal, but usually it's going to have some slight direction one way or the other if it's linear. So positive means it's going up from left to right. Negative means it's going down from left to right. And so if you remember from your algebra days, that would be related to slope, the slope of a line. So positive slope would mean a positive direction. Negative slope would indicate negative direction. So we have form, then we have direction, then we have strength. Strength is how closely the points fall to the form. Okay, so if we have a linear form that we've identified and the points are close to the line, we call it a strong relationship. If we have a linear form and the points are a little bit spaced out, we call it a weak or a weaker relationship. Okay, so at this point, it's subjective. We're using adjectives like strong, stronger, very strong, or very weak. Okay, we're not using numbers yet, but we'll get to that. We'll get to that probably next week. But still, adjectives are fine. They give some idea. They get some ideas across, right? So the strength is how closely the points fall to the form, and for us, mostly the linear form. The last thing I want you to get kind of that I want you to think about with these scatter plots is outliers. And we've already talked about outliers for one-dimensional data. Okay, so if you remember your chapter 4 stuff on exam 3, we had like box plots, and we were looking at outliers in a box plot. That data was for one-dimensional data. That was like number of hours worked, right? And so you just had one number. Everybody had a number of hours that they worked. And so we had the outliers defined by the fences. So hopefully you remember from chapter 4, we had the fences to create outliers. Here, it's a little bit more subjective. We don't really have, at least we're not going to study any fences for two-dimensional data here in chapter 6. There are ways of defining outliers mathematically with formulas, but we're not going to have the time to do that in here. It's not part of our curriculum. So what I'm saying is you look at the data. If you have a point that is obviously out of the trend, then we call it an outlier. If we don't have any points that are out of the trend, we say that there are no outliers. And I'll be the first to admit it's a bit, it's kind of like in the eye of the beholder because we don't have like a mathematical definition here, but it still is useful to use this word. Okay, good. So I'll do one and then I'll have you guys try a couple here. Okay. So let's say we do some kind of go through some sort of observational study or maybe an experiment, and we get our data back. We put it into the scatter plot, and what do we see here? The form is definitely linear. Okay. The direction is negative. The strength is strong. Is it very strong? Maybe, maybe not. In about an hour or so, probably next week, we'll be able to define, we'll have a number that tells us how strong it is. Great, thank you, Anna. Then outliers. I'm not seeing any outliers. What about this one? Not well, maybe, right? But again, it's subjective at this point. But in my view, that would not be an outlier. Okay, so you guys try a couple of these others. Okay, so we have these two data sets here. I want you to comment on the form, the direction, the strength, and the outliers for each of these. Now, one thing the strength is really important. Okay, if the strength is very, very weak, then it sort of undercuts the importance of the other uh, characteristics, right? I mean, if the strength is just so weak, then it's kind of like the data don't really have much of a form at all, right? And they might not have any direction if it's a very weak relationship. So if it's super weak, then it might not even be worth, discussing the other features. Okay, so I'll go quiet for a minute and let you guys give this a try. Just a word or two for each of those characteristics. Okay, so what do you guys think about the second one here? What form would you go with on this? Is it linear or nonlinear? Not linear. Armand's saying linear. Yeah, so I would probably begin actually by thinking about the strength. This is quite weak, right? It's a very weak, I would say weak or even very weak. And when it's very weak again, then it's like the form, it might not have any form at all. So then I would probably say, well, um, so I always kind of do this in a negative kind of way. Are there any nonlinearities? I'm not really seeing like a great, any curvature to the data. I'm not seeing any elbow or break in the data. So since there are no nonlinearities, I know it sounds kind of funny to say that, but since there aren't any nonlinearities, I would probably say it's a linear form, right? I mean, it does kind of look like it's going, more or less kind of in a straight pattern across the x-axis there. But I wouldn't really like, emphasize that too much because it's such a weak relationship. Okay, the direction, uh, maybe if you squint at it, you could say it's kind of going up, but I don't think it's super obvious. I would probably say there's no real association here. Doesn't really appear to be going up or down there. Any outliers? Probably that one, right? Maybe one outlier. Okay. Any questions or concerns about that one? The one on the bottom, I think, is pretty clear though. What kind of form do we see on that bottom one? What do you guys think? It's pretty obviously nonlinear, yes? Good. Thank you, Lana. Yep. So non-linear. Okay. When it's nonlinear, it's not clear what the direction is. Over here, the direction is down. Over here, the direction is up. Over here, the direction is flat. So there's not really a direction when we have some of these nonlinear patterns. Okay. The strength, I would say this is strong. And I would probably say no outliers, although I wouldn't, you know, it's not like something I would, defend too strongly. Maybe these are outliers, right? But they seem to more or less fall in the pattern. Okay, good. Let's keep going. Unless you guys have questions. So in the lecture notes, we have a few pages, several pages of algebra. So I'm going to jump forward a little bit. The algebra doesn't really apply to us so much. So I'm going to jump all the way 10 pages here. I'm going to go to 175 here, all the way to page 6 to section 6.2. Okay, so so we start with the scatter plot, the graph, for helping us analyze relationships between two quantitative variables. Then we're going to go further with it. And in fact, this topic just seems to keep going and going and going and going. It just sort of never ends. There's so much research in linear regression. So many complex ideas, and it's really a useful topic. So so what is linear regression? Linear regression is where we take our scatter plot and we put a straight line over the scatter plot. Okay, so down here we see another scatter plot. That blue line there is a straight line that we call it the linear regression, and we use it to help us understand in a more kind of quantitative way the relationship between those two variables. Okay, so that's the linear regression. It's a line. Then we're back to our two kinds of variables. We've talked about these many times, right? Explanatory variable, response variable. If one is clearly the explanatory variable, then we typically will make that the x variable. And if one is clearly the response variable, we'll typically put that as the y variable or the vertical variable. Okay. The rest of these definitions are better if we come back to them. I don't want to just lay a ton of definitions on you and then I'd rather just kind of do a few, then do some problems, then come back and do some more definitions, do more problems. One thing I do want to talk about is the correlation coefficient. Okay, so earlier we were talking about the strength of a relationship, and I kept saying, well, this is sort of subjective, right? Is it strong? Is it very strong? Is it weak? Well, here with the correlation coefficient, it gives us a single number that we can use to describe the strength of the relationship. So it's no longer subjective, it's nice and objective, okay? And so what is the correlation coefficient? Well, we use R, the letter R, to stand for the correlation coefficient. R, that one number, describes the strength and the direction of a linear relationship between two quantitative variables. So notice that it only works for linear relationships. If you have a nonlinear scatter plot, then the linear correlation coefficient is not the right technique. Okay, so it's only for linear relationships. Then the formula is set up so that it always gives us values somewhere between -1 and +1. Okay, so we can actually use this tripartite sandwiched inequality. R is always between -1 and +1. Okay, so let's practice with this a little bit. We don't need to understand everything about it all at once. Let's kind of ease into our understanding of it here with some example problems. So A through G, we have pairs of quantitative variables, and we're trying to understand the relationship between them. And so just kind of using common economic sense, I want us to see if we can guess if the correlation coefficient is going to be positive or negative. Okay, is the relationship going to be positive or negative between these various pairs of variables? Okay, so I'll do the first one. Let's say we have interest rates on loans and number of cars sold. Okay, so the way I work through these problems is I'll draw a scatter plot and kind of use common sense here a little bit. So what would cause what? Would number of cars sold cause the interest rates, or would interest rates cause cars sold? Probably the interest rate will be the explanatory variable, and number of cars sold would be the response variable. Although if you're good enough with economics, you can probably reverse that, right? So, so what happens to the number of cars sold as the interest rate changes? Well, you know, some people don't even get car loans, they just pay cash for cars. So for people like that, it doesn't matter what happens with the rates. They can go up or down, and it just doesn't matter if you're paying cash. But, you know, lots of people do get car loans, and, you know, if the interest rate goes higher, it's more expensive to get a car loan, right? And then, you know, so some people need the car so much that they'll get the car no matter what the interest rate is. But there are some people, right? There are plenty of people that will respond to interest rate changes, right? They might keep their used car a little bit longer, right, until the rates go down, or they might just, you know, start taking the bus or something, or getting a bike or something, right? So my point is that as the rate increases, the number of cars sold will probably, at least on the margins, it'll go down. And you know, conversely, if the rate goes down, the number of cars sold will tend to increase, right? So what kind of relationship is that? We would call that a negative relationship. Does that make sense? Okay, so we haven't even really talked about how you calculate R, but we're starting to get an idea of what it means, right? So the correlation coefficient would be negative between these two variables. Okay, so we've got several more of these scenarios. I want you to practice with them. So again, let me just kind of dole these out, and I want you to practice here. So Armand, you tried B, Devin, C, Killian, D, Kylie, E, Lana, you do F, Rita, do G, Sarai, you do Sarah, you do B, and then Shoshana, if you could do C, that would be great. Okay, so use kind of, kind of guessing, kind of intuition there, common sense, whatever you want to call it, and see if you think the relationship would be positive or negative. Would the slope of this scatter plot be positive or negative? And when you get your answer, just put it over in the chat there, or just say it out loud. That's fine too. And we'll put these in the lecture notes here. Okay, so Armand is saying negative. Good. So temperature outside and ice cream sales. Let's see here. So what causes what? Probably temperature would cause sales, right? Let's see. I eat some ice cream throughout the year. Even in the winter months, I'll go and eat some ice cream every now and then. But I probably do eat more during the summer, right? Because, well, it's just sort of more present, right? It's just, you go to the park and they have an ice cream store shop open, right? Or the ice cream truck is out in the summer months, right? So just probably on average, I would eat more when it's warmer out. When it's cold, I'll still eat some at the house, but certainly not outside at a park, right? So I think this would actually be a positive relationship. You guys see what I'm saying? Oh, okay, yep, good. So, good. So yeah, again, it's not a perfect relationship, but I would say it would tend to be positive there. As one goes up, the other's probably going to go up. Good. All right, and then let's see here. Did anybody get C, Devin or Kylie? Who's doing that one? It was Shoshana or Devin, I believe, huh? Negative. Okay, number of hours per week on the treadmill and cholesterol level. So what causes what? Probably hours on the treadmill and then cholesterol. So the more time you spend on the treadmill, right? That's the more time you spend working out. And yeah, probably people who are working out more probably have lower cholesterol for various reasons. Again, not perfect, but I think that would tend to be a negative relationship there. So making sense, everyone? Okay, so a negative relationship. Okay, price of a Big Mac and number of fries sold in a week. This is probably the hardest one of them all. Did I give that one to Killian? I think so. Killian is saying negatives. I agree with that. It's not quite as obvious, but they are correlated, right? The number of fries that people get at McDonald's is correlated to the number of Big Macs because that's, pretty much anytime I get a Big Mac, I'm going to get some fries along with it, right? And so if the Big Mac prices were really high, let's just take kind of a crazy example. Let's say they were charging like $50 for a Big Mac. Nobody would buy those, right? Or very few people would buy Big Macs, right? So if those people, instead of going to McDonald's, go to Burger King, right? The McDonald's will probably sell fewer fries. And vice versa, if they had a special where they were giving the Big Macs away for like a dollar, You'd have tons of people in there buying those Big Macs for $1, and while they're there, they'd probably get some fries along with it, right? So I would say that this is probably also a negative relationship. Good. Okay, let's see. Who had, was it Kylie for shoe size and IQ? Any ideas there? Negative? Um, perhaps. Probably the, well, I'll be honest, I'm kind of shorter, and so, for me, I kind of hope that there's no relationship there. Um, but who knows, maybe there is one. So I was kind of thinking no correlation, right? Movie ticket price and number of moviegoers. Lana, are you still here? Did you get that one? Negative. Yep, I believe so. Um, there are some people who will go to the movies no matter how much they cost, but most of us do respond to prices. So, I would never go to a movie if it's like $50, right? Some people would, but a lot of us will not. Whereas if they're like $1, right? They used to have like movie theaters like that back in the day. If they're super cheap, then I'll go to movies more often, right? So that would also be a negative correlation. There's lots of negatives here. Any questions out here? Any questions here about this? Number of years of education and annual salary. Pabrita, what did you say here? Positive? Yeah, I would tend to say positive. This is pretty well established in the data. We all know the story about the person who drops out of high school and still becomes a billionaire. Um, and we know people who get PhDs and then um, don't find jobs. But on average, there is going to be, a positive correlation there. Uh, great. So there we go. We do know some things about R already, more or less. Is it positive or negative? Okay. And so you'll have to use some kind of common sense, some economic common sense on some of these. The next thing we do want to do is really start to get a clearer sense of values for R. Okay. So R is on a spectrum from -1 to +1. And so let me draw you a picture here that I think will help you think about values of R. So let me come back over here, and there's a nice picture that sort of summarizes R values. Okay, the least R can be is -1. The most R can be is +1. So if it's a +1, that means it's a perfect positive relationship between the two variables. So what does perfect positive mean? Perfect positive means if you know one, you can predict the other perfectly. So what does that mean? It's a straight line. Okay, that is a perfect +1 linear correlation. What would perfect -1 mean? Perfect -1 would mean that if you know one variable, you can predict the other perfectly. But because it's negative, it's sloping down. So it's also a straight line, but it's sloping down. Those are the two perfect cases. With with um, with real data, it's very unlikely you would ever get -1 or +1 in the real world. Okay, unless you work in like a physics laboratory or a chemistry laboratory, they might have some of those kinds of data sets. But if you're in the social sciences, if you're doing medical research, it's very unlikely you'd get perfect correlation. But it is still useful to have kind of the those extreme cases in mind. So what's right in the middle? Right in the middle would be R equals 0. So that would be the case where there is no correlation. So what does that look like? A cloud of dots. Okay, so that would be R equals 0. This would be R equals 1. This would be R equals -1. Most data sets are somewhere in between. Okay, they're not perfect relationships, but usually if it's a linear relationship, you can kind of see some kind of pattern there, right? So just want to draw in a couple of intermediate cases. And so that might be maybe r equals negative 0.5, and this might be maybe r equals 0.5. Does that make sense? So I like that graphic. I think it'll help you think about r. Let's use that to finish off this, to look at this example here on page 176. So if you look back in the notes on 176, you basically see something kind of like this, a bunch of different scatter plots, and we're asking you to kind of guess what the correct R value would be. So when I ask you to guess R, there's no way you can really get it super accurate. Okay, so I'm not, like if you had this on the exam, right? It's not like you can guess R to the second decimal place or something, right? So we just wanted to kind of do our best to show our understanding here that R varies between -1 and 1. So let me do maybe one of these, maybe an easy one here. This would be maybe about -1, right? Because it looks like they more or less fall in a straight line and it's a negative relationship. Okay, so you guys do the rest of these. Um, just do your best with guessing, and then I'll show you an applet you can use to kind of refine your sense of what R is, if you'd like. Anybody have an idea for this one here? It's kind of a cloud of dots. Do we see much of a pattern there? What would we think R is for that? Yeah, good. Thanks, Killian. Yeah, it looks like about 0. Okay. How about this one here? Maybe they do kind of jump around slightly, but more or less they're falling in a straight line. So yeah, that's what I'm going here for, right? So maybe it might be 0.999 or something, we don't know, but basically I'm going for about 1 right there. Okay, and then on this one, it's clearly positive, not perfect. So who knows, maybe 0.7. If you want to say 0.4, that would be fine too. I just want you to understand that it's some intermediate value between 0 and 1 there. And then over here, that might be negative 0.7. You guys getting the idea? If you would like, there is an applet. It's kind of a fun little game to play. Well, I don't know how, it's probably not the world's most exciting game, but where is it? Oh, the correlation guessing game. Okay, so you guys know these applets, right? We've, whoops. You remember this website with our Rossmann Chance applet? Okay, so it turns out that they made a ton of these um, interactive websites here. And so what we're going to do for a second is use this to kind of refine our sense for R. Okay, and so what you can do with this is you can ask it to draw a random sample of 25 points. Okay, and then you can guess the correlation. Okay, so clearly this is negative, and I would say it's a moderately strong relationship. So I'd probably say maybe negative 0.7. Okay, and then I can check my guess here. It's actually stronger than I thought. It's negative 0.813. Okay, so let's do another one. Okay, so I'll do a new sample. Let's get maybe a positive one here. So this one is positive. Okay, so 0. It's weaker. It looks weaker than the other one. So maybe, I don't know, maybe 0.3. Okay, and you can see it's about 0.4, so a little bit stronger than I thought. Okay, so if you want, you can have a look at that applet and practice with a few of these, and I think it's probably helpful to get a better sense of R. Okay, so then we have 3 graphs. I want you to ignore this one. The horizontal case is kind of strange with R. It's sort of can be kind of a pathological example. So just take these 3 here, and I want you to rank them from weakest to strongest. So strongest would be a 1, weakest would be a 3. So rank those 1 to 3. 1 is the strongest. Now notice I'm not saying anything about the direction. I'm just saying the strength. And that's another thing that I'd like to capture back here on this picture. Stronger Well, it can be stronger positive, or it can be stronger negative, right? So the closer you are to 1 or to -1, the stronger the relationship. The closer you are to 0, the weaker the relationship. So the absolute value here is relevant, right? So when it comes to strength, it's the absolute value of R. Okay, so let's see. That looks like the strongest. It's very close to +1 there. This one is negative, but the points are pretty strong, pretty close to the line. So I'd say that's the second strongest, and then this one would be the weakest of those three. Any questions there? So how do we actually calculate the linear correlation now? Well, there's a formula for it. Um, it's quite complicated. We decided to not even put it in the lecture notes. I kind of wish we did have it in the lecture notes so I could just point to it and show you. So let's see here. Killian saying, why don't we rank the one that went horizontal? That's a great question. It turns out that for a perfectly horizontal line, the linear correlation can do some really weird things. Okay, so let me just kind of in a minute explain what goes on here. Um, okay, good. So let's see here. If you have the points lying on a straight line and the line is sloping up, then you have a correlation of +1. So this line here would have a correlation of +1. This line here, since since all the points lie perfectly on a line, that would also have correlation 1. Even one with a very slight slope, if the points lie on that line, it's correlation 1. But as soon as the line goes perfectly horizontal, the formula breaks down basically, Killian, and it's undefined actually. Okay, so just even a slight angle, if the points lie on a straight line, the correlation is exactly 1. But as soon as you go perfectly horizontal, things break down on it. So the horizontal case actually kind of breaks the formula a little bit. So that's why I didn't want to do that one. Okay, where's our formula? I just want to show you the formula here. It's right here. Okay, so this is the correlation coefficient. 5, 10 years ago, we used to make students do this by hand, and it's fine, but it just takes up so much time. We opted out of doing this by hand so we could free up some time and do more other stuff. Okay, so there's a formula here for it. And so if you want to do this by hand, you can look this up and give it a try, but it's basically a bunch of z-scores is what it is. Okay, and so if you use this formula, it will always, you're guaranteed, produce a number between -1 and +1. So that's where the formula comes from. What we're going to do instead is use software to calculate it. So we'll use GeoGebra here. And I also want to do an interesting class activity so we can create our own data and then we'll use this to see how to calculate R. Okay, so I really like this activity. It kind of raises some interesting questions and it helps us see how to calculate R. So here's what we're gonna do. We're gonna, if you're willing, you don't have to disclose this information if you don't want to. I I'm I want to look at the relationship between the number of siblings each of us has and the number of aunts and uncles we have. Let me get started. Okay, so I have 3 sisters. Okay, well one I have a half sister and then two full sisters. So I'm just going to say 3 sisters. Okay, so in my family growing up, we had 4 kids, right? Me and then 3 siblings. So I'll just go with 3 for the number of siblings that I have. Then, for number of aunts and uncles, uh, let's see, my mother has or had 3 sisters And then my father had 2 sisters and a brother. Okay, so I have 6 aunts and uncles. Okay, so I'm not including the aunts and uncles from marriage, right? So those 6 aunts and uncles, these are like the people my parents grew up with, right? Not their husbands and wives. Why? What are we doing with this data set? Well, I want to answer a question. Um, so it could be answered in this way. Does the family size one grows up with um, influence the family size that they actually have when they have their own family, right? So everybody grows up, right, in some kind of family, ranging from 0 siblings to more siblings, right? Um, so does the family one grows up with influence the size of the family they have later in life? It's kind of awkward to write it out, but hold on 1 second here. Size of the family one has later in life. Or maybe a better way would say, does the number of kids in one generation affect the number of kids that you have in the next generation? Okay. Or maybe let me ask it another way. If you grow up in a large family, do you tend to have a large family yourself when you establish your own household in the future? If you do, right? So so everybody has some number of siblings, right? Maybe 0, maybe you have 10, maybe you have 3. And then when you get older, you have some number of kids, right? Maybe you have 0 kids, maybe you have 10 kids, maybe you have 3 kids. Does that make sense? So I'm just curious what you guys think. Do you think people who come from large families tend to turn around and have large families again? Do people who come from small families tend to have small families themselves? Or maybe if you grow up in a large family and you hate it, you turn around and don't have any kids of your own, right? Or maybe you grow up in a small family and you didn't like it, so you have lots of kids. Is there any relationship between them? Okay, so how would we answer that kind of question? Well, probably, a lot of you guys, you're in college, right? So maybe, you don't have any kids yet, but maybe in the future you will, right? So we can't really use you guys for um, the number of kids yet, right? Because probably some of you will have kids in the future. So the best generation to use would be your parents' generation, right? Because probably most of you, your parents are done having kids, right? Maybe you'll have another brother or sister come along, but probably not. I guess, right? Definitely not my parents. My parents are not going to have any more kids, right? So our parents' generation is the right generation here because we can count the number of siblings they had, right? So between my 2 parents, they had 6 siblings, and then my parents turned around and had 3 kids of their own. Does that make sense? Well, 4, I guess, with me. But so these 2 numbers here uh, are give us an idea of how large my parents' generation was, right? How large their families were that they grew up in, and then the number of siblings I have is sort of a measurement for how many kids my parents had. Does that make sense? So if you're willing, if you would go ahead and just put those numbers over in the chat. If you don't want to do this, it's fine. Great. And again, don't use the aunts and uncles your aunts and uncles married, right? It's just the number of it's the aunts and uncles your parents grew up with, basically, right? And I realize that sometimes these situations can be very fluid and complex, so just kind of do your best at estimating these numbers here. So um, great. So we have a data set going here. Any questions about this? So now the question is there a relationship? Okay, so do people who grow up with large families, do they tend to have larger families or not? Okay. So that's what we can answer here with this small data set. Now it's very small, right? It's obvious it's probably too small to do real science. And plus this is a convenient sample. So It's not like, we're not going to publish our results here or anything, but still I think we can get a nice idea of R. So let's take this over to GeoGebra and have a look here. Okay, so we'll go to GeoGebra. Let's see here. Here's GeoGebra. And then we go to the toggle, the three dots, and we go to spreadsheet. And we have to get the data into GeoGebra, right? So here is our data set. Okay, so 3, 1, 1, 3, 2, and then 6, 3, 7, 11, 5. Okay, so how do we calculate R? Well, we have to highlight the data. Okay, so we highlight the data in the spreadsheet. Then we go over to the histogram here. We go to two variable regression analysis. Right? Everybody has two numbers. You have a number of siblings and then you have a number of aunts and uncles. So the scatter plot does seem to indicate there's some kind of positive relationship. Again, 5 is such a small data set that we probably, we can't really do real inference here about the whole population, but among our sample, it does appear to be positive. People who come from larger families do seem to turn around and have larger families themselves. Okay, what's the strength of that? It's obviously not a perfectly strong super strong relationship. So to get R, we come over here to the sigma x, and we have it right here. Okay, so we go sigma x, and then we have R right here, 0.5899. So 0.5899. Okay, so 0.5899. Okay, and so how strong is that? Well, it is positive. If we come back over here, 0.5 is about right here. So our R value was a little bit stronger than 0.5. So it's moderately strong relationship there between the two variables. But again, it's just for our sample, right? It's a small sample, so we can't do inference based on that. Good. So what are you guys thinking? Does that kind of make sense? Then it asks a question here. It says, compute the residual for the third student in the data set. What on earth is a residual? Well, that's one of those things I skipped over. So let's go back and talk about residual. What does residual mean in everyday conversation? If you talk about a residual, it's something that's left over, right? So with the linear regression, what we'll do is we'll have a scatter plot, and then we'll put a line through the data. Right, so we take a line and we draw a line that we think best captures the relationship. When we do that, each point is going to have a distance from the line. Okay, and so we call that distance the residual. It's how much is left over. Okay, so the model is predicting this. The data is saying it's actually this. The residual is how much distance there is between expected or predicted and the actual value. That's called a residual. Okay, and so we define residual up here. The residual, which is E, also known as an error, right? It's the difference between observed and predicted. Okay, so we're out of time. We're at 12:50 now, so we'll pick back up with this idea of the residual on Tuesday. Yeah, so we're in a great spot here with the calendar. So Tuesday we'll come back and we'll continue on with our chapter 6. Thursday we'll have Thanksgiving, and then after that we'll be in our last week of the semester. So things are wrapping up here quickly. Do you guys have any last questions as we break for the day? Anything I can help you with? No? All right. Well, have a good one, guys. Have a nice weekend, and I'll see you back here on Tuesday.